Section 10.1 has to do with now comparing two proportions. This is where we are going to be doing a confidence interval for the difference in proportions of two different populations. So very similar to 8.2, except instead of looking at the interval for just one proportion, now I'm looking at the interval for the difference in two proportions for two different populations. So introductory example. At school 1, 70% of a simple random sample of students did their homework last night, and only 50% of a simple random sample of 200 students at school 2 did their homework last night. Estimate for what the difference of the proportions of all students of those two schools in terms of how many of them did their homework last night. So we can tell that just between these two samples I have a 20% difference. But what would it be if I had access to the population's worth of data? How big of a difference between the two schools would there be? We know based on our sampling distributions from last unit that when we have the difference between two distributions, the shape will be approximately normal as long as n times p and n times 1 minus p, or in this case p hat, is at least 10. For this section, we will need to do that for both samples, both proportions. So I would have to do 70% times 100, 70, and 30% times 100, and likewise for the others. There will be another option for that. We'll talk about that in just a minute. The center will be at the average difference in the sample proportions, and then the spread will be the deviation of the combined spreads for each distribution. So the distribution for the first proportion is the standard error calculation. This is the standard deviation for the second proportion in the second sample. When I combine them, the difference, the standard deviation for the combined distributions would be this. Notice that we had to, even though we were subtracting, we would end up adding on this side. Now this formula is on the formula sheet, more or less, with most of the others on this, the third page of the formula sheet. So there's your standard error for sample mean, sample proportion, difference of sample means. Here we go, difference of sample proportions. Here's the formula. Notice it's p instead of p hat, but essentially that at least means you don't have to memorize that large formula. The conditions will need both samples to be random or randomized from a randomized experiment. The 10% condition needs to hold for each or for both of the samples, not just for one, or the results from both of the experiments should be independent of one another. Here is the approximate normality or the normal condition, the n times p hat, n times 1 minus p hat. All of these have to be greater than or equal to 10. Some books will say 5 here once again, but our book, I believe, uses 10. The formula, the point estimate for the difference will be just the difference in the proportions from the sample. Plus or minus, we're going to go back to z here because once again it's proportions. So just like 8.2, we're going to use the z star value we get from our chart, that last line of the t-table, and then the standard error calculation that I mentioned a minute ago. So here's our example we're going to work through. Teens versus adults on social media. This is from 2009, so it's been a little while ago. 800 U.S. teens were surveyed, and 73% of the teens said they use social networking sites. 2,253 U.S. adults were surveyed, and 47% of the adults said they use them. So I wish to estimate with 95% confidence the average difference, actually I shouldn't say average here because we're talking about proportions, so the difference in proportions of teens versus adults who use social media. This is a 2 proportion z interval, so it does matter that you specify this is a different interval than what we did in 8.2. The samples were both randomly selected and be considered independent since The sample size of teens is less than 1/10 of all U.S. teens. The sample size of adults, likewise, less than 1/10 of all U.S. adults. The distribution is approximately normal. Notice I see all the n times p's and n times 1 minus p's are all greater than 10. Then I plug in my values, so teens minus adults, plus or minus. There's the teens plus the adults, all under the root, and I get the interval between 0.223 and 0.297. You can also write that as between 22.3% and 29.7%. So I'm 95% confident that the interval between 22.3% and 29.7% captures the true difference in proportions of social media use between teens and adults. Okay, here it is on the calculator. Notice that 2 proportions the interval is a different option. So we would go there, choose for the 584 of the 800 teens use social media. Notice we had to figure out what 70% of the 800 teens were, because we weren't given the 584, but we just figure out 70% of the 800 sample size. If when you do that, so if you do 0.7 times 800, if it ends up being a decimal, go ahead and round. So x, both of the x's have to be whole numbers. It can't be decimals. Both the n's have to be whole numbers, no decimals as well. Put in the confidence level, hit calculate, and you get the same result that we got from our calculator once you round. From the original formula is what I meant to say. Okay, another example, comparing the proportions of children who come to school without eating breakfast in 2 different low-income elementary schools. 80 students from school 1 found that 19 had not eaten breakfast. At school 2, 150 students were surveyed, 26 did not eat breakfast. Do the data give convincing evidence that there's a difference in the population? So we're going to do a confidence interval for the difference in proportions here. Notice confidence level is not given. We just fall back to 95% as our default. So I wish to estimate with 95% confidence the difference in the proportion of students who do not eat breakfast between school 1 and school 2. And I need to specify which way I'm subtracting. Okay, notice I did go ahead and calculate my P1 and P2 up at the very beginning. It's not necessary to do here, but like I said previously, I do like positive numbers when I'm subtracting. So since I'm going to subtract, I would rather subtract the larger one minus the smaller one. So I go ahead and figure that out early on. This is a 2 proportion z interval, part of the plan step or the do step, whichever you want to put it. Both the samples were randomly selected and we can't consider independent because of the 10% condition. The normal condition is met because, and here is my n times p's and n times 1 minus p's, all greater than 10. Just like with before, if 1 happened to be too small, I would point that out and either say condition not met or proceed with caution, but I would continue to do the problem. So here is my P1 minus P2 plus or minus. The z-score for 95% is 1.96, and then put each p hat times 1 minus p hat over the sample size, combine them under the root for the standard error, and I get between negative 0.047 and 0.1754, so I'm 95% confident that the interval between those 2 values captures the true difference in proportions. Once again, ignore the word average here. True difference in proportions of students who don't eat breakfast between school 1 and school 2. So keep in mind here, if I'm looking at a difference, I'm usually interested, quite often I'm interested in whether 0 was included, because 0 would indicate that there is no difference. So since 0 is included in this interval, in other words, since the interval spans all the way from the negatives to the positives, I cannot say that there is any statistical difference or any evidence statistically that there is a difference between the 2 schools, even though there was a small difference in the sample proportions. It wasn't big enough to enable me to say that there is a difference in the population proportions. Okay, so we did an activity in class. We combined M&Ms versus Skittles. We had to combine blue M&Ms versus purple Skittles because we didn't have the same color. So they had some candy that they got that day. They had candy data from a couple of classes together, and then they chose what colors they wanted to look at, and just to see if there was a difference. Notice that all 3 of these intervals span both negatives to positives. which indicates that there is no distinct difference, for instance, between the proportion of blue M&Ms versus purple Skittles, or orange M&Ms versus orange Skittles, yellow M&Ms versus yellow Skittles. Or at least we don't have statistical evidence for it. Okay, so go ahead and take a look at the problems from 10.1 and let me know if you have any questions.